How does Big Bang predict the birth of our universe? Who proposed this theory? What was before the Big Bang? How this vast universe started from just a small hot ball? Which elements were the first to come into existence? Okay, be patient. All these doubts will be cleared along with many more, but you have to stay with KNOW. No, till the end of this video. Do consider subscribing KNOW No and press the bell icon and stay tuned for more interesting and science related videos with beautiful graphics. The Big Bang theory states that all of the current and past matter in the universe came into existence at the same time, roughly 13.8 billion years ago. At this time, all matter was compacted into a very small ball with infinite density and intense heat called a singularity. Suddenly, the singularity began expanding and the universe as we know it began. This theory was proposed by Georges Lemaître, a Belgian cosmologist and a Catholic priest, in 1931. The Big Bang is an attempt to explain how the universe developed from a very tiny dense state into what it is today. It doesn't attempt to explain what initiated the creation of the universe or what came before the Big Bang or even what lies outside the universe. At the earliest moments of the Big Bang, the universe was so small that classical physics didn't apply to it. Instead, quantum physics were in play. Quantum physics deal with the physics on a subatomic scale. At 10 raised to the power minus 43 seconds, the universe was incredibly small, dense and hot. This homogeneous area of the universe spanned a region of only 10 raised to the power minus 33 centimeters. During this phase, matter and energy were inseparable. The four primary forces of the universe were also a united force. The temperature of this universe was 10 raised to the power 32 degrees Kelvin. As tiny fractions of a second passed, the universe expanded rapidly. This rapid expansion of universe is referred as inflation. The universe doubled in size several times in less than a second. As the universe expanded, it cooled. At around 10 raised to the power minus 35 seconds, matter and energy decoupled. This is known as baryogenesis. During baryogenesis, the universe filled with a nearly equal amount of matter and antimatter. There was more matter than antimatter, so while most particles and antiparticles annihilated each other, some particles survived. A period of particle cosmology followed the quantum age. This period starts at 10 raised to the power minus 11 seconds. During this time, the unified force broke down into components. The forces of electromagnetism and weak nuclear force split off. Photons outnumbered matter particles, but the universe was too dense for light to shine within it. The period of stranded cosmology followed the period of particle cosmology, which begins at 0.01 seconds after the beginning of the Big Bang. During this era, the universe continued to expand and cool, and the subatomic particles formed during baryogenesis began to bond together. They formed neutrons and protons. By the time a full second had passed, these particles could form the nuclei of light elements like hydrogen in the form of its isotope deuterium, helium, and lithium. This process is known as nucleosynthesis, but the universe was still too dense and hot for electrons to join these nuclei and form stable atoms. As you saw that, a lot happened in the first second of the Big Bang, but that's just the beginning of the story. After 100 seconds, the universe temperature cooled to 1 billion degrees Kelvin. Subatomic particles continued to combine. By mass, the distribution of the elements was approximately 75% hydrogen nuclei and 24% helium nuclei. The other percent consisted of other light elements like lithium. The temperature of the universe was still too high for electrons to bond with nuclei. Instead, electrons collided with other subatomic particles called positrons, creating more photons. The universe continued to expand and cool. After about 56,000 years, the universe had cooled to 9,000 degrees Kelvin. At this time, the density of the matter distribution in the universe matched the density of radiation. After another 324,000 years, the universe had expanded enough to cool down to 3,000 degrees Kelvin. Finally, protons and electrons could combine to form neutral hydrogen atoms. It was at this time, 380,000 years after the initial event, when the universe became transparent. Light could shine throughout the universe. For the next 100 million years or so, the universe continued to expand and cool. Small gravitational fluctuations caused particles of matter to cluster together. Gravity caused gases in the universe to collapse into tight pockets. As gases contract, they become more dense and hot. Some 100 to 200 billion years after the initial creation of the universe, stars formed from these pockets of gas. Stars began to cluster together to form galaxies. Eventually, some stars went supernova. As the stars exploded, they ejected matter across the universe. This matter included all the heavier elements we find in nature, everything up to uranium. Galaxies in turn formed their own clusters. Our own solar system formed around 4.6 billion years ago. Today, the temperature of the universe is 2.725 degrees Kelvin, which is only a couple of degrees above absolute zero. The homogeneous section of the universe we can theorize about reaches 1 into 10 raised to the power 29 centimeters. That's larger than what we are able to physically observe using our most advanced astronomical instruments.